So today we're going to take a look at the concept of what you want to do when you're writing programs. We'll talk a little bit about algorithm design and optimizing code and tools you might use to help you in that process. And then we'll also talk a little bit about object-oriented programming. So there are lots of different ways of doing the same thing. We've seen that sort of an emerging theme throughout the course. This isn't just a statement about Python having lots of different ways to accomplish the same low-level task, but also the statement that there's lots of different fundamental ways to approach getting a solution to any given problem. So I'm going to discuss first this Scrabble algorithm. Hopefully you're all at least kind of vaguely familiar with the game of Scrabble. You have 7 tiles in front of you, and your goal is to make words out of the 7 tiles and then fit them in on the board. So we're not going to take this all the way to the extreme and talk about how to figure out where on the board you could put the word. We're just going to consider the problem of I have 7 letters in front of me. How would I make all possible words out of those 7 letters and validate that they're actually words? So if you looked at the sort of draft of the book that I put out there, this is also one of the examples that I use in the book because it's a nice programming problem and it helps introduce some new concepts. So let's say we have this set of 7 letters. How many valid words could we make out of them? It turns out there are 68 of them. So what approaches might we use to solve that problem? Well, how many possible words might there be? So if we have 7 different letters, we could have 7-letter words, and we could have 6-letter words, and so on. So basically that's 7 factorial plus 7 factorial over 1 factorial, et cetera, et cetera. So the number of permutations there is basically 13,699 possible total words. Great, so how could we check and see which of those words might be valid? So different approaches that we could make. One approach would be to make every possible word from the list of letters that we have, and then check to see if each of those possible words is in some dictionary of valid words. We could do that in a couple of different approaches, which we'll talk about. And then there's the opposite approach, which is to look through the dictionary and check every word in the dictionary to see whether you can make that word from the available set of letters. So 2 completely opposite ways of looking at the problem. So let's talk about the first approach first. So design number 1, we'll ask the user for the list of letters. Right. So we'll ask the user for the letters that they have in their tiles. We'll need to have some source of valid words. So we'll just assume that we have a text file that contains a list of all words that we will consider valid. So you can get a dictionary file from anywhere you like. Then we have a nested loop to make each possible word from the available letters. Inside that loop, we'll check to see if each word that we create is real. And if it is real, well, then we'll add it to a list of valid words. And at the end, we'll just sort the list and print it out. All right, so here is a program that will accomplish that task. You can see it's a fairly long program, and it's a little complicated. So how might we go about taking code like this? Let's try it first. So let's go ahead and put it into Jupyter. You see it even spans more than a screen at the scale that I've got here. If I run it, it'll ask me for words, or for letters, and we'll enter our 7 letters, and then let it run. You can see it's still running there, and eventually it'll come back. So the program works. We'll see results in a minute, but figuring out how it works would take a lot of reading through the code and trying to understand. It would be really useful if, for example, we could go to a particular point in the program and be able to interrogate what the values are there. That'll help us develop an understanding for the program. So, debugging. If you write a program and the program doesn't work, what do you do about it? Sometimes it'll be obvious. If you make a syntax error or something like that, then you'll try and run it, and Python will give you an immediate error message and say, oh, all right, I have a stupid syntax error there. That sort of error is obviously pretty straightforward to fix. But what if you make a logical error in the program, and the program runs, but the answer it gives you isn't the correct answer? How do you go about figuring it out? Well, you'll need to sort of trace what's happening in the program at different places. So how would you go about interrogating what's happening in the middle of your program? The easiest approach, of course, would be to just use print statements in your program. You can add print statements at various places and have them print out intermediate values. But of course, if you've got a loop inside a loop inside a loop inside a loop, and you put a print statement in the innermost loop, that means that you're going to have thousands of lines of stuff getting printed out on the screen, which is pretty annoying and frustrating. There's also a module which can be very useful, which is the traceback module, and that allows you at any point in the code. So print exe will print an exception. So if you use try and except, instead of having the program crash, you can have the except block do something, and in that except block you can print the exception that caused the crash. Traceback also allows you to print a stack trace at any given moment in the code, which will tell you how the program got to where it is at that point in the code. So the traceback module has some useful features, but really these are not as useful as we might like them to be. So there are lots of tools out there for doing what's called debugging. In other words, getting rid of bugs in your program. Jupyter isn't the only solution to this sort of programming problem. There's another tool provided in Anaconda called Spider, which is an integrated programming environment. Doesn't go through the web browser. It's a real program. It has an editor, and it has a debugger built in, and a bunch of other tools. You've got Spider, which is a nice, completely separate tool, has nothing to do with Jupyter. You've got Visual Python. That was a collaboration with Microsoft to put this together. You can install that in Anaconda as well. But now, very recently, Jupyter has actually started adding this modular concept to Jupyter Labs, and now has a debugger that you can integrate into Jupyter Labs. So we'll just take a quick look at that today. This is brand new this year because, well, it didn't exist. Well, it existed last year, but last year it was just a real pain to get it installed and get it working. Now it's a little bit easier, although you still have to do a couple of steps. One thing I haven't mentioned before is Anaconda. We've done conda install and various packages. There's also the concept of channels in Anaconda, which is other sources of software. So if you just say conda install, it's only bringing in packages which are part of the main Anaconda branch, which is put together by the company that makes Anaconda, and it's very reliable, well-tested stuff. There's another another environment, another channel for Anaconda called Conda Forge, which is for user-provided packages. So there's a big community of Anaconda users who puts together other open source packages and makes them compatible with Anaconda. And you'll often find sort of more cutting-edge stuff there. So if you want to use this, I highly recommend installing the Jupyter Lab from Conda Forge instead of the Jupyter Lab from the main Python distribution. You can, even if you have Jupyter Lab already installed, which obviously do, if you do this, it'll overwrite that one with this one. Then you have to install this other tool called Node.js, and Node.js has to be a fairly recent version of Node.js. If you just say conda install Node.js, it'll give you a slightly older version. So you need to actually specify the version number right now. Now the stuff that I'm telling you about installation probably will change over the next year. As this becomes more stable, it will probably work its way into the main Anaconda distribution. But right now, if you want to install this debugging module, you have to go through these steps here. Once we've got it installed, you will find that your interface is a little different. Okay, so if you look over here, if you're using a current version of Jupyter, you'll see this little puzzle piece icon on the left here. So if you go to this puzzle piece icon after you've installed the latest version of Jupyter Lab, you'll find that there's this list of add-ons that you can include in your Jupyter environment, and one of these is Jupyter Lab Debugger. So I've already installed that in my environment here, but so after you've gone through the steps I showed there, you also have to find it in here and click the install button to enable that module in your environment. Once you've done that, what you'll see is this new sort of switch over here and this new icon over here. So if I turn this on, it'll bring up a set of 4 panes on the right side of my browser here. And the panes each have a different purpose within this environment. The top pane is extremely useful. It will show you all of the variables in your current environment and what they currently are, and as it executes code, it'll update that. Okay? It won't update it live while your code is running. It'll wait till it finishes a block, but after the block finishes, then it'll update all the current variables. Most variable browsers, you'll find this in all the debuggers, have some way of sort of suppressing stuff that you don't care about. For example, if I import math, I may see the entire set of math libraries listed here under variables, and that can be annoying. You can see that it has little arrows for expanding and contracting things in certain cases, but it may show you more stuff than you want sometimes. Then down below, you'll see some other things. It has breakpoints, source, call stack. So we'll see how that works. So here's our program. Let's take a look at the program first, and then we'll play with the debugger. So we ask the user for letters. I've got a file in my local file system called words.scrabble, which is a list of it's just a text file which contains 1 word per line. If we look here, so you can see this is just a dictionary file. It contains all English words, and it's not limited to 7-letter words either. It's just a big dictionary. So it opens words.scrabble. It reads them all into an array, and then it just processes them slightly. It makes everything lowercase. It strips off the new line at the end and that sort of thing. So basically, words is now a list of all valid English words. Then we enter this function, this loop inside a loop inside a loop. You can see it's a loop that's nested 7 layers deep. Now it's probably fairly obvious, since we've got a loop nested 7 layers deep, that in some fashion each layer of that loop is responsible for 1 letter in the final word. How is this working? Okay, so for n equals 0 in range 7, so I'm looping over 7 different values. And I'm assigning those values to the first element in n, and then I'm assigning it to, right? So, all right, this is a number. Right, so you can see it's already looking kind of complicated, right? We've got this n of 0 inside letters, and you really would need to figure out what's going on. So, how are we going to look at that? Well, we could put print statements in there, but if I put print statements in here, then as I said, you'll get massive numbers of lines of output. So what we want to do instead is, now that I've enabled the debugger, you'll see something appearing over here. Each line in the program, you can see this little red dot. Okay? Now, if I go to a particular line and I click on the red dot, now you'll see it appears over here, breakpoints. And let's do it at another point too. Let's do it maybe here. All right, so it set these 2 breakpoints, and now if I run the code, so let me execute my block of code again. It's going to ask me for letters again. So you can see that as soon as it got to this line, you can see it's highlighted now. It stopped the program, and the variables got updated. So I can see the state of all the variables now. So right here in the program, W is equal to P, and words is a list, which is all right. So the words hasn't been overwritten yet, so we don't want to look at words. Words is from the last time I ran something. Anyway, so you can see all the variables at that point in the program. So if I press the play button here, it will continue running the program from the point it's at. So it paused the program here, but didn't stop it. It just paused it. So if I hit play, it'll continue. If I press this button, it will take 1 step. It'll step to the next point in the program, and it'll stop again. So I can step one step at a time through the program that way. And then there are other options for doing it in various ways. If I want to just terminate the job, stop it, so I can make some change to the code or something, I can hit the stop button. So if I hit play, it'll go until it gets to the next breakpoint, and then stop, and then it'll update all of the variables here and that sort of thing. So you can see this allows you to interrogate what's going on in the program, right? And I can just continue playing and stopping and playing and stopping. It'll stop every time it gets to one of these breakpoints. So you can see here it's going through the second breakpoint over and over again, but that's because it's looping 7 times. So if I do this 8 times, then it'll wind up back at this first breakpoint. Okay? So let's go ahead and turn off the 2 breakpoints, and then we can play, and then it'll just continue running again. Right? So this is a great tool to go in and figure out exactly how programs are working and to help you solve problems when something's embedded deep into a recursive loop or something like that. All right. One other thing that's really useful when you're trying to get your code to work optimally is profilers. So the question is, we learned earlier that if you want to time how long something takes, you can use the time it thing, and you can see how long some piece of code takes to work. But that's a very imprecise measure, right? So if you want to say, okay, how long does my program take? You make some changes. Okay, how long does it take to run now? Did I improve things or not? It's great. But if you say, my program is taking 60 seconds to run, and it seems like it should be done in less than a second, why is it taking so long? Well, then you want to be able to figure out what's going on at every point in your program to help you figure out what's making it take so much time. So that's what profiling is about. So there are various ways of profiling code. Again, so if you use Spider, it has a profiler built in. Python language itself has a couple of built-in profilers, profile, cprofile, hotshot. There's another module called line profiler, which we're going to talk more about in a minute. And then in some cases, if you're doing things like say you're using one of the image processing libraries that we were talking about before, it may be that you run your profiling in Python and you discover that, oh, well, I'm making this call to this particular image processing routine, and that's taking 99.9% of the time in my program. So I need to understand now what's going on in the C code. What's happening in there that's making that take so much time. So there are profilers that you can use at the C level in combination with the Python level and get more detail. Now this is obviously only useful if you're writing the C code too. But anyway, that capability does exist. Now if you're using Jupyter, it turns out again there's some nice convenience functions for profiling. So there's a built-in in Jupyter called prun, which will allow you to see how long a function takes to run, and it'll check all the function calls that are made during this function, right? So if you've defined your own function and you've called other functions inside that function, every time you make a function call, it'll count that call, and it'll tell you how long the call took to make and that sort of thing. So let's try that, and we'll see how it looks. So this program, it's taking a fairly long time to run. We didn't actually see it, but it was taking something like 30 or 40 seconds to run, which seems like a pretty long time for this relatively simple sort of task that we're doing. So we've got exactly the same program, but now instead of just find words, I'm saying prun find words. So I can actually just make that change here. Oops. Oh, sorry, I didn't make it a function. So I have taken this block of loops here, and I've put them inside a function instead of just being at the root level in Python, and then I'm calling the function. So I did make that change to the code. So let's do that. And then here, we'll paste the new code in there. Okay, I'm going to turn off the debuggers so we get rid of that stuff on the side. Sorry. It's not letting me select what I want to select. There we go. Okay, there we go. So this is the code that now has the prun version, and we can run that and type our letters, and when this finishes running, which again is going to take 30 or 40 seconds, then we'll get some additional output. So we'll just wait for that this time. Actually, while that's running, let's go back here, and I'll just introduce the next one, which is the line profiler. So this profiles your code at the level of function calls. So every time a function gets called, whether it's a function you've defined or a function that's sort of built into Python, it counts it and keeps track of it. The line profiler, on the other hand, will look at every line of your code and count how long that takes to run every time it gets executed. So if you have a loop inside a loop inside a loop, it'll count, all of those nested executions of that line every time it gets to it. But the line profiler isn't built in, so you have to use Anaconda to install the line profiler, and then inside Jupyter you have to load the extension for the line profiler, and then you use this LP run instead of P run. So it's got line profiler run like this, and you can look at the line profiling. So we'll do that in a second as soon as this is done. Okay. So here's our output. If we scroll down after the list of words, you'll see now we have this additional stuff that it dumped out, which is there were 88,215 function calls in that code, and then it'll tell you statistics for each one. So it'll tell you the number of times each function was called. It'll tell you the total time which was used by that function when it was being executed. Then it will also give you cumulative time, and that is how long did the function that was called take to run, plus all the stuff that it called, right? So this is just telling you how long that particular function took. This is telling you how long the stuff inside the function took as well. It'll tell you how long it took for each call of the function. Right, so this is total, this is per call, then total and per call in two different ways. So anyway, this gives you some idea of what's going on. But if you'll look, you can see it took 41 seconds to run the code, but if we look at all these other function calls in here, none of them took a very significant amount of time. So it didn't actually answer our question, right? It told us how long the main function, the find words function, took, but it didn't tell us why it took so long. Something that's in our code itself is taking all of that time up. So this is where we can use the line profiler. So let's give that a try. So we'll do this load ext line profiler. Let me just do that below. Oh, all right, fine. I must have loaded it earlier. And then here, where we have prun, we're going to change that to lprun -f find words. So we have to give it the name of the function that we're going to call, and then we do the actual function call with the parameters. Okay. I'm just going to get rid of the final print statement here. We don't care about that anyway. I mean, we don't need to see the word output. We're just trying to figure out what's going on. All right, so we'll let that run again, and again we're going to have to wait 41 seconds or so for it to finish. The line profiler actually may have a little bit more overhead than the normal profiler, so it may make the program take longer to run because it has to do all the counting and stuff like that. But hopefully it won't take too much longer to run. So we'll just give that a minute. Let's see, I don't think there's... Yeah, right, okay. Okay, not too bad. All right, so now we can see line number. So each line in our code, then the number of times that line of code got executed, the amount of time that line of code was spent in that line of code, and what we'll see is line 12, 16, 20, and so on seem to be taking most of the time. So what the heck's going on in our program in line 12? So if we go up here in the editor and we enable, view, and we enable line numbers, we can see line 12 is this. So if the word that we've created is in the list of words, then we append it to the list. So it's spending most of its time searching the list of words to see if the word is a good word or not. Anything we could do to make that more efficient? Any ideas what you might do to make that more efficient? So words right now is a list of all of the available words in our dictionary. When you search a list for an element, it has to loop over every element in the list and see if it's equal. You remember that there's another data type in Python, which is the set. And sets have the ability of checking membership very, very quickly, because instead of looping over all the values, they use something called a hash. So when you add something to a set, it generates a hash for that item, and then it can check for hash membership much more efficiently. So we're just going to say words equals. Actually, we'll just do it in place here. We'll just say words equals set words, and now let's try running the code. Oh, look, it's done. So just that one tiny change, changing a list into a set, made our program take 100. It was 100 times faster, or something like that. Okay, so that's the first lesson. Data types can matter, and the profiler can help you identify places in your code that could be optimized. Maybe. I mean, it isn't always going to be the case that there's something you can do about it. Okay, now we've got this program. This program is complicated, right? So, I mean, basically we've got our outer loop, which is varying the first letter to all possible values. Then for all possible first letters, we try all possible second letters. And for all possible first and second letters, we try all possible third letters. You can see it's a nested loop. Nested loop, nested loop, nested loop. And we've got one nesting layer for every letter in our final word. And we also, of course, if we want to be able to look at words that are only 1 letter long or 2 letters long or 3 letters long, at each layer we also have to check to see if the shorter word is a member of the valid words list, right? So at each layer we're building another letter to our word, and we're checking the short word to see whether it's a member of the list of words. But what happens if we only are provided 5 letters? This program will only work if you give it a list of 7 letters, because it's looping over all 7. Now you could probably put an if statement in at each level too, which said, oh, if I don't have any more letters available, then don't do the loop layers below that, and that would be okay for anything less than 7. But if you wanted to be able to deal with 20-letter words, then you'd have to make a nested loop 20 layers deep, which is not great. So what can we do to get around that? So there's a programming concept we haven't introduced yet, and it has somewhat limited uses, but in the cases where it's useful, it is the only way of approaching the problem in a practical way. So when we run into a problem like we just had, recursion is the correct solution to that problem. What is recursion? Recursion is a function that calls itself. Recursion is inherently kind of dangerous. If you don't write your code very carefully, it's easy to end up with a function that calls itself forever, and it gets stuck. And that can cause all sorts of problems. There were all sorts of stories in the early days about people physically crashing computers by accidentally running recursive programs that didn't have stopping conditions. In Python, it's a little more careful about it. If you have a recursive program in Python that goes past some level of recursion, it'll automatically kill the program and say you did something bad. But that level is actually pretty deep, so it's not a situation you really want to wind up in. So if we look at a simple example, this is a factorial function. Is a function that you can write either recursively or non-recursively. So if you write the factorial function non-recursively, say you have a value x, you can simply loop over all of the values less than x, and for each value you multiply it by the current value, right? So just factorial 10 is 10 times 9 times 8 times 7 times 6, etc. So here we're starting with a low number, so it's 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10. Here's the recursive form of the function. So in the recursive form of the function, if you call it with 10, it checks to see if the number that you called it with was 1. And if it was 1, then it returns 1. If it wasn't 1, then it returns x times the result of calling the function again with x minus 1. So you can see what this is going to do. If I start with, say, 3, it's going to be 3. And it's going to take 3 times, then it's going to call itself with 2. Then that function is going to get down here, and it's going to return 2 times, and then it's going to call itself again. It'll get to 1, and that'll return 1. So you'll have 2 times 1, and then that'll return to the first loop, which will multiply that by 3, and it'll all collapse back down. So basically, if you had 10 here, it would call itself, and it would get 10 layers deep, and then it would collapse back down to 0 and give you your answer. Okay? So it's a little tricky to understand, but it can make certain programs much, much more efficient. So now we're going to do the same thing, but we're going to use recursion to make each possible word instead of using nested loops to make each possible word. So here's our new version of the program. Now I've got the place where we ask for the letters and we read the list of valid words and stuff like that at the bottom, and we've got our function definition up here at the top. And the function that we have here is called all good words. So you call it with letters. You call it with a list of words. In this case, is the list of valid words. So it can just sort of internally check whether the words are good or not. And then it's also passing the result list in. So what's going to happen when we call this function? So one way of doing this is you could have all good words, and then you could call it, and you could do the checking yourself on the words that you got back from it. In this case, we're having the all good words function generate the words and check them at the same time. Okay, so when we get into all good words, it has a list of letters, it has a list of valid words, and it has a list of results. There's also this partial option here, which you don't call when you call the function yourself, but when all good words calls itself, it's going to be making use of this partial thing. So what are we doing here? So if the length of letters is 0, then we return. This is the end of our recursive loop. So as soon as we don't have any more letters to use, we stop. Then we loop over all of the letters. We add L, which is the current letter, to partial. What's going on with that? Well, partial is basically, so when I go through the loop the first time, partial is nothing. It's just an empty string. So possible here then just becomes the first letter, just becomes L. If that one letter is in words, then it just adds it to the result list. If it's, when possible. Oh yeah, right, fine. So if it's a valid word, then it adds it to the results list. You'll notice that when we add it to the results list, we add a tuple, which is the length of the word followed by the word itself. That's just so we can sort it easily at the end. There are other ways you can approach that, but that's nice and easy. Okay, now we have shorter. Shorter is going to be a copy of the list of letters that we got as an input, and then we remove the letter that we just used. Okay, so here when we're doing this loop, we're going to use the first letter, and we're going to add that to possible. Then we're going to make a shorter list, which is the list without the letter that we just used, and then it's going to call all good words itself, along with the word, the one letter word that we started there. So when this loop when this function calls itself, now possible is going to contain one letter, and then when we go through the loop here, it's only going to be looping over 6 letters, because when it got called here, it was called with the shorter list of letters. So it's going to loop over 6 letters, but it's going to start with partial having the first letter already set. And then when it gets here, it'll call itself again, and that'll be the 3rd letter, 4th letter, and so on. So this function will keep calling itself until there's nothing left in the list of letters, and then it collapses back down again. And at that point, we should have already built up our list of answers. So we can try this. And the advantage of this is, of course, that it can handle any number of letters that we want to give it. It doesn't require 7. So we can start with our 7. We could also just say those. Or we could use 8 or 9 or 10, however many we wanted. And it'll just go until it runs out of letters and then stop. So we've added some additional capabilities in addition to making the program a lot easier to look at and deal with. All right, third design. So in the third design, we're flipping things on their on its head. We still have to ask the user for letters, and as we'll see in a second, this approach, unlike the other approach, so one of the features in the Scrabble game is that there are a couple of blank letters, and the blank letter can be any letter you want it to be. So when we're going through the program this way, we don't really have a very good way of dealing with blanks. We could add another loop outside this loop, and if we encounter a blank, then we could loop over each possible letter. But that would mean that if you have, say, 2 blanks in your list of 7 words, the number of permutations has now grown massively, right? It's the number we had before multiplied by 26 squared. So we just have this humongous list. So it becomes really inefficient code. It would take a lot longer to run. So even our speeded up version of the program wouldn't be great that way. So when we do it this way, when we go through the list of valid words and we check to see if we can make it from the list of letters, then now dealing with the blanks is easy, right? Because a blank can represent, so you check to see, I need the letter Q. Is Q in my list of available letters? If it is, then I take it out of the list of letters and I look at the next letter, and that may be a W. Is there a W in my list of letters? Well, if there's no W but there's a blank, then I can use the blank. So I can match it as sort of a wildcard. So here's our program for handling it this way, and you can see actually it's a pretty simple, it's a sort of simpler looking program, right? So now I just have a function called goodWord. This is just going to check one word. So it gets the word and it gets the list of letters, and then it basically loops over all the letters and sees if it can make it. And then we have our little block here. So the question mark is going to be what we use for the blank. So if there's a question mark in there and we don't find the actual letter itself, then we'll use up the question mark instead. And if we get all the way to the end of this without breaking, then we return true. Okay, meaning we successfully did it. So you'll note we have a continue here and we have a continue here. So it only gets to this return false if it failed to find the letter. And then here we're just going to loop over all of the, here we're just going to loop over all of the, here we're going to loop over all the words, here we're going to print the results. Okay. So let's try that version of the program. Okay, and again we get the same list of words out. And I can put a question mark in instead of M, and now of course we get a lot more words out because there's obviously a lot more words you can make. So I could put multiple question marks in there and everything will work fine. All right, so if we look at the final results, our initial nested loop approach took 42 seconds to run. Once we converted that list to a set, it went down to 0.44 seconds, which is obviously a big improvement. The recursive approach was even better. That was 0.38 seconds. Not much of a speed up, but the program was nicer. And then if we try the check all words approach, it actually took longer. It took 0.9 seconds. However, we added the question mark functionality, which we didn't have up here, and this probably wouldn't be the same for different lengths of words, right? If we made 10-letter words, then this check all words approach would only take very slightly more time, and this approach would take a lot longer to run. So the scaling of this approach versus this approach isn't the same. But as long as if you're talking about only 7 letters and you don't need blanks, then this would be the much more efficient approach. If you need blanks, then you do this, and if the words are longer, then this again. So that's how we would go about optimizing our little Scrabble program. So we've got one more problem to talk about this module, This is a classic example from programming class. Every introductory programming class in existence talks about prime numbers at some point in time. So our goal here is to generate a list of all of the prime numbers less than 100,000. So let's think about this in the standard terms. We've been using all term. How do we represent the data? Well, it's basically just going to be a list containing the prime numbers. Nothing complicated there. Break the task into small pieces. Okay, well, we can loop over all possible prime numbers, check to see if the number is prime. To check to see if the number is prime, we have to check all of the possible factors to see if it's divisible by each of those. If it is divisible by, if it is prime, so if it's not divisible by any of those factors, then we add it to the list, and then we just have to write the program. So here is the straightforward program to find all the prime numbers less than 100,000. So we loop over all possible prime numbers, then we loop over all possible factors. Obviously, we don't use 1 as a factor, and we don't use the number itself as a factor because it's always going to be divisible by 1 and itself, but we can use everything else. So if it finds that the remainder when you do an integer division is 0, then that means it was divisible, and then we break. If it wasn't divisible and we can loop, if we get through this entire loop without anything, then we can print the prime number out. So here we're making use of this for else construct that we talked about briefly but haven't used very much. The else only happens if it successfully makes it through the loop without break. So let's give this a quick shot. I have timing results that we'll be talking about. So I'm going to modify the program so it doesn't print 100, so we only go up to, say, 10,000, just to avoid filling my web browser with stuff. Anyway, so there it is. There's all the prime numbers less than 10,000. Okay, if you did it to 100,000, it takes a little while to run. Maybe there's some opportunities for making this program more efficient. Any quick ideas? How you'd make that more efficient? You see anything there which might be redundant? Well, all right. So this is just timing. Yeah, don't worry about the timing loop. Anyway, so it took 41.5 seconds to run if we did it up to 100,000. Obviously, took a lot less than that with 10,000. Okay, so if we look at this loop, you'll see this term frequently in programming, scales as order of n squared. Basically, that means that as you increase the number of values that you're searching or looking for, the program will take n squared more time to run. So if I go to 1,000,000 from 100,000, it's going to take 100 times longer to run, not 10 times longer to run. So there's some stuff that we're doing here that we don't need to do. So what if we skip even numbers, which are also divisible by 2? I mean, if it's divisible by 2, then any even numbers are going to, once we've checked 2, we don't have to check any of the other even numbers, right? So here we can improve that a little bit. We can change our range to, so we'll just add the initial primes to the list to avoid any complexities there. But here we can skip every other number that way. So that'll make our program run 4 times faster. Because we're also skipping even numbers in the numbers we check. Because if it's even, then we know it's not going to be a prime. Okay, so we can make it 4 times faster that way. What else could we do? Well, we really only need to check for the first prime factor. If the number you're checking is 21, that's 3 times 7, and if it's not divisible by 3, it's not going to be divisible by 7, right? So we don't need to actually go all the way up to the number itself, or even half the number itself. We actually can stop once we get to the square root of the number, because you're going to have to find one one factor in less than the square root of the number if it has any factors at all. So we'll go from 3, because we're avoiding the initial primes which we're just seeding it with. So we're going to go from 3 to the square root of the number plus 1. The plus 1 is just for, odd cases where the square root eliminates the value that we're actually after. And again, we can step by 2. So that makes a massive speed improvement, right? Now it only scales as order of n to the 1.5 power. So we've made the program a lot faster, particularly if we're going to make really big lists of prime. Now it only takes 0.13 seconds to run. Well, we still haven't really simplified things all the way. Really, and you should have had a hint to this already when we eliminated 2 from consideration. We only need to consider factors which are themselves prime numbers. Right? Once we've eliminated 3 as a factor, we've also eliminated 9 as a factor, and 12 as a factor, and 15 as a factor. Right? It would have to be divisible by 3 if it were divisible by any of those things. So instead of this loop here, looping over all possible values from a range, now we're just going to loop over the list of prime numbers that we've already determined. Oh, wait, took 4 seconds now. Oh, it seems like I should have been much more efficient, right? I went from 0.13 seconds to 4. What the heck happened? Well, I forgot the square root. Right? So it's not that I need to check all prime numbers. I only need to check prime numbers that are less than the square root of the number. So we add this little trick in here now. So now we check the prime numbers to see if each prime number to see if it's less than the square root of the number. And if it is, then we go up to that point. Now we do this in a tricky way. So as the number we don't have to continue. We don't have to start this check from 0 each time. We start from where we were with the last prime number that we were checking, and then we just possibly increment that by 1 the next time we go through the loop. So anyway, we keep this running pointer, which is basically the largest prime number that we need to consider as a possible factor for each value. So that worked. So once we do that, now it only takes 0.09 seconds to run, which is faster than the 0.13 seconds that we had before here. So we've made an additional improvement. All right, great. So less than 0.1 seconds, and we can get all the prime numbers less than 100,000. That's not too bad, but maybe there's a completely, like the Scrabble problem, maybe there's a completely different way we could approach the problem. Is there some way we could turn this problem on its head? Anyone have any ideas? Think about ways that you could kind of invert the problem. So right now, we're looping over every possible number and asking, is that number prime? So it turns out that the solution to this, the alternative solution to this, is actually over 2,000 years old. A guy named Eratosthenes was thinking about prime numbers and said, well, the best way of coming up with a list of prime numbers is to write down every possible number, and then I'm going to cross out all the multiples of 2, and then I'm going to cross out all the multiples of 3, and I'm going to cross out all the multiples of 5, and it's basically starting with all numbers and then eliminating periodic sequences with the periodicity of every prime that's below it. So we start out with a set, and then we loop over all of the prime numbers that are less than the square root of 100,000, and we exclude all of the multiples of that number from the set. So we basically start with a set that has everything, and then we go through and we throw out everything we know isn't a prime, and everything that's left must be prime. And it turns out that this, for 100,000, takes 0.03 seconds. So it's 3 times faster than that other algorithm that we're using in this case. Now, most programming problems that you have, there's almost always a way of kind of taking the problem and flipping it around and looking at it the other way. Which of the 2 approaches is going to be faster? There's no good way of predicting in advance. It depends completely on the problem, and in some case, it'll depend on the limits of the problem. So it may be that this is faster for 100,000, but for 10 million, it may be that the other approach is faster, right? You have to look at the behavior of the algorithm to sort of decide which one is going to be the best way. But by not thinking about the problem both ways, you won't necessarily come up with the most efficient solution to the problem. It turns out there's one other fault here. So the Sieve of Eratosthenes is great if you want to take find all of the prime numbers less than 100,000. But if you want to find all the prime numbers between 1 billion and 2 billion, it doesn't do quite as well. And the same thing with the other program, right? There are, we're sort of assuming that we're starting at 0 and working our way up, because then we're building up the list of all the primes that we already have. The requirements of the program will change with the aim of what you're trying to accomplish. All right, here is an example of a one-line program which finds all the prime numbers less than 100,000. We use our list constructors to achieve this. So you can see that we're build up a list of all the possible numbers, and then here, if it's in anyway, you can read the code if you want to figure out exactly how it works. But we can take this code and run it, and it's actually pretty fast. Now, question. Here's a one-line program which can achieve the same thing that we achieved with this program or with this program. Which of these programs is better? Assume this one's the fastest. Now I've got this version of the program. It's a lot shorter. Is it better? So there's something known, it's been around for a long time, as the Obfuscated C contest. They do this every so many years. It's not always done on a regular basis. I'm not sure if it's actually still going on. I haven't checked in a few years. But the goal was to produce a C program which does something interesting, but is as difficult to read as possible. And generally, you wouldn't be able to even figure it out if you looked at it. Here is an example of one of the winning entries from some years ago. This is valid C code. You could put that into a C compiler, compile it, and run it. And if you run it, it produces an image file on disk, which looks like that. So this program is actually a full ray tracer, which can generate ray traced spheres in color and produce this readable image. I think it's a PPM image or something like that. So it's an easy file format. Anyway. So there are lots of cool examples in there of the winners of the program. I don't think anyone would say, though, if you were writing a ray tracer, that you should try and make it look like that. There's also Obfuscated Python. This is actually a valid Python 2 program. Now you might say, well, what about indentation? That can't be right. Well, it turns out Python 2 didn't care too much whether you over-indented or under-indented and stuff, so it actually is valid Python 2 code. And as you may guess based on the shape, this produces fractals. The point that I'm trying to make here is that efficiency in your code doesn't necessarily mean elegance in your code. So this is a term you'll hear frequently if you talk to programmers. Is it elegant code? Elegant code is code which does what it's supposed to do computationally efficiently, and the code is also easy to read and easy to understand conceptually. Now, sometimes you run into an example of some function which is considered elegant code because it's clever. And it does something in a way that you just wouldn't think is possible. There's a famous example of that, which I don't have here, but in one of the earliest first-person shooter games, when back before we had these high-end graphics processor cards and stuff like that, it was really hard to get enough computational power out to do this sort of 3D rendering stuff. And a guy came up with a really clever way of computing a mathematical function faster than the processor could compute it itself. It had limited accuracy, but it had enough accuracy to make good renderings on the screen. And people still use that example as in programming classes as, wow, this guy just came up with something completely off the wall and clever. That's considered elegant code, even though if you looked at the code, there's no way in the world you would figure out how it does what it claims to do. But generally speaking, you should strive to write code more like this, which is readable, has comments in it, and you can understand conceptually. If you can make the program 10 times faster and it becomes a little less readable, well, maybe that's a reasonable trade-off to make, right? But if you make the program, if you do what we did here, and the program actually becomes a little bit slower, but it becomes shorter, then that's not a reasonable trade-off to make. Anyway, so that's it for this module. We've got one other module to go through today.